not long ago, a year or so, Christos showed me a paper by Iwao Hasakawa, where there was a very nice reminding to me what I neglected 30 years ago. I thought it is a very elementary, trivial thing, so I just neglected it. Because I wrote a lot of simple algebra, and this is what has been done. I did it in 70s or whatever. And then Vladimir Sabelnikov reminded me that he did it also sometime in 94. And the story is like that. Well, I skipped this and also this. Well, this is also a reminding, so I will not go on with that. Now, what happened essentially, that Hosokawa essentially found a very nice, simple kinematic relation, which we did too long ago, but neglected this. And if you use this relation with these definitions, you find that this is essentially a law which is equivalent to the Kolmogorov law. But the great but, which I realized becoming 30 years older, is that this shows a correlation between a large and a small, if R is not large, say, quantity. So it means that you can make an interpretation of this relation as a correlation between large and small scales, so a kind of non-local behavior if you interpret it as a couple between large and small scales and bidirectional one, because if the correlation is non-zero, it's a sign that something happens. So, and this essentially prompted us to, so this is what has been, this is what I told, and this is what Hosokawa also wrote, though his paper was essentially mostly devoted to something else. This was not the main point. Well, anyway, so what we did, because we have a very extensive set of data, we just went and made a check of this just to make sure, just to be we were interested. Now there were several motivations. This is the conventional 4-5 law representation, and this is just using this relation, equivalent one. Now what you realize immediately, that some bad behavior becomes good, and the reason for that is instrumental, of course, because in here you have a velocity difference in power 1. Whereas here you have, of course, in power 3. It's delta U cube. Now, this thing is a bad set of data obtained in atmospheric measurements in using aircraft. And when you use an aircraft given by somebody, you are supposed not to check the time you want to fly and the place. They just allocate you the time and place, and you fly in a place where there was almost no turbulence. But we found a bit, and this is what we got. But the experiment was, of course, very interesting and very useful, and we had lots of lessons. But so far we couldn't implement them anymore because funding is not so easy for such an endeavor. Anyway, this is just the beginning, which we published in our Physics of Fluids paper not so long ago. I believe this year even. And but just to remind you a little bit about experiments, what it was. These are the history, our Israeli station. This is the flight. And this is a real thing, and this is where the probes were, and we made beautiful measurements with extremely good resolution, and that's why we were successful, because the level of turbulence was very low. And this is the experiment of made in Switzerland, in a very beautiful valley nearby how you call it? St. Moritz, yeah. And there is a beautiful wind tunnel, really, between two mountains, having such a wind tunnel for granted nothing. It's amazing, because having to use similar things, for instance, in NASA Ames, costs $2,100 per day. Well, we could measure all kinds of things which are not relevant here. Just for your knowledge, you may look just in the papers, lots of stuff. And this is just how it looks like. It's just doesn't matter. I mean, this is the thing which can measure in a volume of 3 millimeter or so all the velocity derivatives, no Taylor hypothesis, and also temperature derivatives. Not so good. It requires just money to improve it. Anyway, what we wanted to do next is to understand a little bit more about essentially the kinematics, because the main point in my presentation today is just to stress the role of kinematic relations, pure ones, just simple stuff, elementary, which is amazing. So if you use this relation, you can find out that sum of this and this, if you make a simple algebra, you can find that this thing essentially is a sum of this and this, but before averaging. So, and this can be interpreted in terms of Hosokawa relation as what? What?
It's textbook relation.
Yeah, absolutely. But this is non-local, and this is local. And so you can say that it's even less than textbook. But this is not the point. The point is that having this thing, you can check this carefully, and you can see that essentially if the contribution from this and from that comes in a different signs, so the non-local stuff in this representation produces for you, it essentially cancels part of that and results on this. Okay? Now, it's a trivial matter, and you can check it. For instance, we can check this non-local relation as I displayed right before. Usually, it happens following the Murphy law, that it works not so bad, yeah. And this is again an indication of the non-local interactions. Now, one can say that, okay, but you have here 2-point information, one in one point, another one, and you can blame that maybe if you use. But the point is that you can produce far more relations of that kind. You can say write any structure function, a standard one, as delta U in power, as represented by a sum of terms which all of them are correlation between large and small scale quantities, all of them. And the collection of these relations is available on the web, so you can have a look on that. And for instance, these are the relations, and you can check some of them. Now, what is important here, and why it is so interesting? Just because if you don't have non-local stuff like that, for instance, if there is statistical independence between small and large scales. By the way, look here. It's these are brought. This is a version which has single point here. This is a single point quantity. No more sums. It's a different kind of relation, and it is important to remove some blames that we are not so good. Having these things, if there is there is a statistical independence between large and small quantities, which you see here, then all of these guys will be just zero. So in this sense, without non-local interactions, there is no turbulence in terms of structure function. Everything is just zero. And this relates directly to the sweeping decorrelation hypothesis. If it is true, then of course all these quantities are just zero, or almost zero. Okay? So I exaggerate deliberately, but this is the point. Now, these are just some checks of the relations I pointed. And to get to the sweeping decorrelation hypothesis, I bring you a very simple relation. Let's look at this, which you can write either this way or that way. And by the way, to check the quality of our data, you can see how these relations are seen here. Now, if the sweeping decorrelation hypothesis is true, then at least for small r's, not too large ones, both these things should be zero. But it couldn't happen, because this is not. It's a trivial case. It's a trivial example, but it is important. Also, if you look, if you go back to, I don't know, for instance, to this one, then if the sweeping decorrelation hypothesis is true, then this thing should be equal to zero, because large and small scales are statistically independent in sweeping decorrelation hypothesis. But it is obviously not true. So, and then the last thing is, well, I believe that essentially I will stop in order. I deliberately shorten this because I want discussion. I don't like when there is almost no discussion. So these are the conclusions, well, I believe that at the level of simple, purely kinematic, exact relations for isotropic turbulent flows, you have important non-local aspects demonstrated. And I would say that essentially without non-locality understood as it's written here, there is just no turbulence, because you have seen what I mean by that. Now, in some limited sense, one can speak about separating local and non-local contributions, as I showed on the example of the Hosokawa relation. But in fact, it's probably meaningless, because you can write up these things in many different ways. So what is local is non-local, either in the context of what I'm talking about. And of course, all the kinematic relations I showed you stand in direct contradiction with what is called sweeping decorrelation hypothesis. Now, I'm ready to be attacked. Sweeping? What is sweeping decorrelation hypothesis? You know what is sweeping decorrelation hypothesis? It's independence, statistically, roughly saying, it's independence of small and large scales.
Whose hypothesis is it?
Huh?
Whose hypothesis is it?
Wait. It's a long history of that. But I mean, I can give a bit more information on that a bit later. But okay. Wait.
Look, Kolmogorov for fifth law is u1 squared u2 equal to 1/6 of whatever. Call it whatever you want. It's u1 squared u2 equal to epsilon r. That's Kolmogorov law. So you may say u1, u2 are large scale quantities. But I mean, this u1 squared u times u2 brackets equal to epsilon r with a factor something 1/6. Call it whatever you want. I mean, there is no small scale quantity or large. There are 2-point correlations.
Yes.
That's it. You have 2-point correlations. But it's odd order. You cannot decouple it into large, small, or small scale. It's a velocity squared here and velocity there.
Well, I fully agree with you, but I cannot, but everybody does it.
It's, you can say many words. It's a simple.
Okay, let's take a question.
Over here.
Yeah. But can you please show the correlation you said should be 0 or
Which one? There are many.
the 1 over 30 or
Well, there are many of
in,
them.
what you call the that.
You want this one?
Yeah, you said that
This is a
this
2.40
should be
kilohertz.
0 or very small. But the thing is that it is already very small. This is, I mean, the
You mean that R is small here, yeah?
yeah, but I mean, if you normalize by for example U3 there, the kinetic energy or something, you see that this is already small when R is much smaller than the integral scale. So it's already fulfilled.
No.
The condition is fulfilled. It is
No.
small. It is sufficient.
No? No? First of all, this law here, for instance, is not fulfilled only for small r. If you take this at this end, at this edge, you will see that it is not that small.
But
So-
R is still smaller than the integral length scale. So if you normalize this,
No, it's
in-
not
in a way, in a
it's-
proper
at
way
this
with the-
age, it's already very much comparable. So we can argue about that, but if you speak about Kolmogorov, it's okay, but we can speak about something very much simpler. This one is the simplest kinematic relation you can deliberately brought here. And if there is a statistical independence between large and small scales, people use this wording, then this should be 0, and this is not. Okay? Now come on.
Since you wanted to be attacked, I'll try to get
Come on.
Greg, you pass already.
Okay, well, I to be honest, I don't see the point. I mean, I just downloaded that paper of that fellow. I mean, it's more or less a trivial relation which we always use when you go from a multi-point correlation to a structure function back and forth.
I don't claim it's non-trivial.
It's called Newton's binom. You know this.
No,
Yeah.
it's absolutely.
It's not called hazard.
It's absolutely trivial. We don't have to waste time on that. It's trivial. I do agree with that. I started from that. This is also trivial, a bit less, but it's all trivial. It's elementary algebra. That's why 30 years ago I neglected it. But when I started to rethink it, I realized that it has something in it.
Okay, Greg.
I mean, I liked Hosokawa's paper when I saw it, but I didn't see it had such alarming consequences as you seem to believe. I mean, first of all, you use the term local interaction, which it's not what you're showing at all. You're showing you talk about non-local interaction. This is nothing dynamic. What you're seeing is a non-local correlation.
Yeah,
The
okay.
non-local correlations can be created by local interactions in the sense of Kolmogorov. In fact, Kolmogorov 1962, if you use a multiplier, will create correlation between a large scale and a small scale. Because as you go down the chain,
Terminologically, you
always
are
gonna
correct. Yeah, but okay.
So it's completely.
So the word interaction should be related to dynamics. This is what you say.
Yeah. Well, first of all,
But non-zero correlations between large and small scale quantities have a dynamical significance either.
Well, I mean,
This is what I'm trying to say.
I mean, Kolmogorov 1962 has a correlation between the large scale and the small scale.
Okay.
The multiplier does not.
Thank you,
I
Greg.
just want to, maybe looking at that Hasegawa relation slightly differently. I mean, when R tends to 0, then the correlator tends to 0. So you can say the higher the scale separation is, the more sweeping this correlation works.
Yeah, but that's correct. That's nice. But if you use not really rigorous argumentation, but a little bit of hand waving, then you can say the following. If you use a little bit of standard hand waving, what you see here that this is scaling just like u, if r is not large, small enough as you want, small. That is just u. And this is scaling again, hand waving, like r 1/3. But this is scaling like r. So again, there is a problem, there is a difference. So there is far more than that. Now, if you do the same kind of hand waving argument as I did now, with different relations, which I showed you, yeah, you will get far more than that. You will get far more contradictions. For instance, if you go to relations of higher order, you will find out that, again, in every case, you get something else, different. But I deliberately did it because I like to give justice to people as much as I can. This relation shows you elementarily that if r is close to 0, this is just u squared. And this is scaling like r 1/3. But this is scaling like r. So where we are, it requires a bit more.
Faster, right?
It requires a bit more delicate.
Just calculate. Let's speak again.